Hi, everybody. I'm Taylor. I'm a computer science and economics major, and I'm going to share my presentation live. So my project is Game Plan, the use of classification algorithms in a goal-setting application for young adults and with intellectual and developmental disabilities. A little bit about Game Plan is that it was actually initially a pen and paper methodology developed here at Sargent College to help these young adults transition into independent living by providing them with a toolkit of plans and steps to help stick to their goals and create plans that they're able to follow. This project recently received a grant to fund mobile application development, and this was actually done here again at the Hariri Institute to help them develop an initial version of the app. So the problem with this application right now is that it currently is only designed to feature a hard-coded list of goals for the user to choose from. This means that users aren't able to set custom goals relevant to their own needs. And my goal was to help develop a functionality that allows users to customize their goals in the Game Plan application. So in the bottom, as you can see, users would be able to type in their own goal, and then this would help lead them to a screen with relevant barriers that they can pick to work on. So their interaction with the app is a little bit more tailored to their own interests. So I've included an example workflow of what this might look like. So there are 4 categories in the application. These are work, school, fun, and leisure. So for example, a user could input something that might not be included in the app, something like I want to work at the school library. The app will classify this as a work-related goal, and because of this, they might prompt them with a suggested step 1, such as ask for help with my resume. The first step in creating a classification algorithm was building a data set and vectorizing the data. So when I actually received this project, there wasn't really a data set in place to work with, so I had to make sure that I created sufficient example sentences for each goal category so I could have a wide scope of data to work with. And when we work with data, we need to work with numbers because you can't run algorithms or mathematical functions on a sentence with words. You need to transform these into number values. I did this by creating these sentences as vectors. In the image below, you can kind of see what a sentence vector might look like. 2 sentences that are relatively similar might be pretty close together in a graph, whereas a sentence totally unrelated might be on the opposite axis. My second step was splitting data into test, train, and cross-validation sets. This is so you can test the data and then later train it to classify sentences that it hasn't been exposed to so it gets practice. I followed a pretty standard split of 80% of data in the training set. I also use a cross-validation set, which essentially continuously picks bits of data from the training set and includes it in the test set. This is a standard practice to avoid overfitting of my classification models. I've included a visual to kind of explain how this data might be captured in the test set. So the first algorithm I looked at was a KNearest neighbor model. What this does is it takes a sentence vector and it classifies it as work, school, self, or leisure based off of the categories of the sentence vectors closest to it. So in order to determine the maximum amount of neighbors that I should be comparing each sentence to, I created a graph with accuracy as a function of k. I found that the most accurate point was with k equals 5 when I was comparing a sentence to its 5 closest neighbors. The next model I looked at was an SVC classification model. These are also known as support vector machines, which essentially try to maximize the empty space between 2 distinct classes. This was a lot of trial and error. I was fitting my model as a function of a parameter that tells us how accurate we want our model to be versus how large we want this gap to be when splitting up sentences into these 4 categories. Because this is susceptible to overfitting, I did use my cross-validation data set to mitigate this issue. I've included an image that shows how lines should be drawn, and the larger the C-value is, the smaller the gap is between classes. Similar to the approach I took with my KNN algorithm, I graphed accuracy of SVM as a function of this penalty parameter. I found that my model was most significantly accurate with a C-value of 15, and then after that, the accuracy started to level off. The final step in creating my classification algorithm was to create a voting system. What a voting system essentially does is it takes a sentence vector and it runs each algorithm on it, and the majority vote category is the assignment to that sentence. So for example, if a sentence had 2 votes for the fun category, it'll be categorized as a sentence or goal that falls under the category of fun. However, if there's a split or a tie between 2 categories, the algorithm will lean towards the one single algorithm with a higher accuracy score. So what this project leaves is a really good building block for a model that can be built to learn from misclassification of a user's input and for other integrations of machine learning in the application, such as suggesting steps towards achieving goals or resolving potential roadblocks that might not be included as hard-coded suggestions in the app, but might have been previous inputs or successful attempts from other students who are using the app. Finally, I just want to give a big thank you to my advisor, Dora Erdos, as well as Professors Dario Wahaya and Lance Scaletti, who helped me a lot with figuring out how to approach this big problem. So thank you, and I'm open to questions.